All right, guys. So here we are. We are starting our new unit on rational functions. This question is not in your note packet. So what I want you to do is just take a minute, graph the function that you see on your calculator. So take out Desmos, take out your TI, whatever. So if I'm going to ask you, if I were to ask you to graph this without your calculator, what information would you need, and how would you find it? So take a look at the graph, examine the important characteristics, and then make a little list of what you think you would need to find, and maybe jot some ideas of how you would find it without your calculator. So go ahead and do that now. I'm going to pause, and we'll get back together in a minute. All right, so this is obviously a little different. This is something I usually do in class. You're on your own right now, but here's a list that I think my class came up with last year. So the things that are special about this graph are the asymptotes. All right, so those points where the graph, whoa, that's bad. The points where the graph just comes close to but doesn't quite hit that value, kind of like a log function or an exponential function. The x-intercepts, or the roots, are important. The y-intercept is important. We know the y-intercept happens when x is 0. Domain restrictions. So in this particular graph, x can be 3 or negative 3. We know that by looking at the denominator. We talked about end behavior a lot in our polynomials unit. So what is happening at the ends of this graph is also extremely important. So hopefully you got some of that stuff on your list. We will practice, obviously, working with all this. But if you were able to get the majority of this list, that's really all we need. So this is what we're going to be looking at algebraically without the use of our calculator to graph rational functions. So first, let's describe what they are. Let's just make sure we're all on the same page. So rational functions are functions that can be expressed as a polynomial divided by another polynomial. So p of x divided by h of x, whatever you want to call them, that's what a rational function is. Unlike polynomials, the domain is all values of x except those that make the denominator equal to 0. All right, so this is all written in your note packet. There's some examples of rational functions. So this we kind of tie back to x to the 0 power as being a polynomial. So this is a rational function, even though there's no x term in the numerator. All right, so it's a polynomial divided by another polynomial. Non-rational functions, where the square root has the x term under it. Absolute values, exponential functions, none of those are rational. So let's compare. As we just mentioned, the domain is different. Polynomial functions are continuous. You can draw them without picking up your pencil. Rational functions are not continuous. They may have holes or asymptotes. Polynomial functions cannot be simplified. When I say simplify, I mean nothing can divide out. We can't make the terms any less complicated. We can factor it, but we can't simplify. Rational functions, we do want to look to simplify. Polynomial functions can have exactly one y-intercept. They do have exactly one y-intercept. And rational functions may not always have one. So if x equals 0, where that y-intercept occurs, if there's a hole or an asymptote there, then this graph may not have a y-intercept. So I'm going to get through some of these notes. We may or may not finish everything to get ready for next class, but we're going to get a head start on it. So here's what we need to do when we graph. Most of the stuff we just kind of briefly hit on. First thing, let's factor and simplify the numerator and denominator. So are there any terms that can divide out? So can anything divide out? We'll talk about that a little more next class. The x-intercepts. So what are the x-intercepts? It's when y equals 0. when the output of my function is 0. Okay, so where do they show up algebraically? Or I'm sorry, graphically? They show up obviously on the, well, not obviously, they show up on the x-axis, right? There's where the roots are, the x-intercepts. They show up on the x-axis. How would you find them algebraically? We want to make the output of our function equal 0. So to do that algebraically with a fraction, we know the fraction is equal to 0 when the numerator equals 0. So just so you can kind of see it in front of you, let's say I have a function that says x minus 2 over x plus 3. And I want to find the roots of this function. I want to say, okay, when is this stuff equal to 0? And a fraction equals 0 when the numerator is equal to 0. So for this rational function, the root would be x equals 2. The x-intercept would be the point 2, 0. All right, so hopefully that makes sense. The zeros or roots of a rational function is when the output is 0, and the output is 0 when the numerator is equal to 0. Y-intercepts. We've done this a million times in your math life. What are the y-intercepts? It's where it hits the x-axis. They show up graphically, not the x-axis, the y-axis. They show up graphically, I guess I'll just put that down there. They show up graphically where the graph hits the y-axis, and algebraically, they happen when x equals 0. So the y-intercepts, what we can do is we just plug in 0 for x. All right, if I take this example and bring it back down here, if I wanted to find the y-intercept of this function, I can just put 0 in for x. So I'm left with negative 2 over 3. That would be my y-intercept of this graph. So kind of a nice little shortcut. You could just plug in 0 for all your x's, but all we have to really look at is the constants. So the constant in the numerator and the constant in the denominator, and that's kind of a nice little shortcut to see what the y-intercepts are. All right, so x-intercepts is when y equals 0. Y-intercepts are when x equals 0. Next, the vertical asymptotes. So these occur when a function is undefined. So when is a rational function undefined? Rational functions are undefined when the denominator equals 0. So to find the vertical asymptotes, what we're going to do is find the zeros of the denominator. So set the denominator equal to 0. All right, and I think we will talk about this next class, but this is what a vertical asymptote would look like. So as the graph comes towards that vertical asymptote, either from the left or from the right, we want to ask ourselves, what is happening to our function? Is it trending upwards? Is it getting bigger and bigger and bigger? Or is it getting smaller and smaller and smaller? So you can ignore, well, I'll just block it out. What we're going to do is to make ourselves a little chart. So we want to figure out what's happening to our function as x approaches the vertical asymptote from the left and from the right. And we're going to have some notation for that. We're going to have a little minus sign, meaning what's happening as it approaches from the left. We're going to have a plus sign when we're asking what's happening as it approaches from the right. And you know what? We can do this. We have time. I just don't want to make the video too long. So let's take a look. This is our function that I want to work with, x over x minus 1. So let me get my red arrows out of here for now. X over x minus 1. So first of all, we can kind of go through our process. We can say, okay, what's the x-intercept? What's the y-intercept? So the x-intercept would be x equals 0. The y-intercept would also be 0. The vertical asymptote is when the denominator equals 0. So in this case, my vertical asymptote is at the point, or the line x equals 1. So we need to figure out what's happening on either side of this asymptote? Is it getting pushed upwards on either side, or is it getting pushed downwards on either side? And that's where this little chart's going to come in handy. So what we're going to practice with a lot next class is this. We're just going to make a tiny little table of values. I'm going to put my vertical asymptote in the middle. So when x equals 1, we know this function is undefined. We need to know what's happening just to the left of 1 and just to the right of 1. So I'm going to evaluate at 0.9999. I'm going to evaluate at 1.0000001. So really all we need to do, we don't need an exact value. We just need to know if this is an overall positive or negative output. So if I put 0.99999 in for my numerator, that's a positive value. If I put 0.999999999 in for my denominator, it becomes just barely negative, right? 0.999999999 minus 1 is, negative 0.000001. So this becomes a negative denominator. So when I have a positive divided by a negative, it gives us a negative output. So the overall sign here is negative. That tells me when I'm approaching this vertical asymptote from the left-hand side, so as we get closer to 1 from the left-hand side, my output is going to be more and more and more and more negative. All right? At 1, we know this is undefined. Nothing happens at 1. This function does not exist. And then we can do the same thing on the right-hand side. So we're going to evaluate. We need to know if this graph, there's the bell. We need to know if this graph is going upwards or downwards on the right-hand side of 1. So I'm going to do the same thing. I'm going to plug in 1.00001 in my numerator. I'm going to plug in 1.0001 in my denominator. And again, the actual values don't matter. We just need to know if this is a positive or a negative output. So the numerator is positive. 1.000001 minus 1 is very small, but it's still positive. So here we have a positive number divided by a really tiny but still positive number. And that output gives me a really large positive number. Remember what division is? We talked about this a little bit earlier in the year. It's how many times does this fit into my numerator. So the smaller the denominator gets, the bigger this output is, right? A number divided by a super tiny number, 0.00001, goes into that 1.0001 a lot of times. All right, and it's an overall positive value. So as we approach my vertical asymptote, x equals 1, from the right-hand side, so as we're getting closer to 1 from this way, my function is getting more and more and more and more and more and more and more positive. So we're going to state this intermediate behavior. And here's our new notation. So this is read as x approaches 1 from the left-hand side. That's what that negative means. So as x approaches 1 from the left-hand side, this graph could come like this. All right, my board just locked up on me. Hope you're back with me now. So anyway, what I was saying, as we approach from this left-hand side, depending on what this graph looks like, we'll do that next class. It could come like this and come straight down there. It could come more from down here and then turn straight down. It could come through and somewhere up here, whatever. But as we get closer and closer and closer to our vertical asymptote, to 1 from the left-hand side, this graph is going to turn downwards. And then the opposite, based on our chart, the opposite is going to happen from the right-hand side. So as x approaches 1 from the right, so that's what that symbol there means. As x approaches 1 from the positive side or from the right-hand side, the y values approach positive infinity. So as I'm coming from this way, the graph is going to hit that vertical asymptote and it's going to turn upwards and just go screaming more and more and more positive. It could come from down here. If there's an x-intercept here, we could turn up this way. But that's kind of the main, well, not the main, that's three of our first steps to getting these rational functions graphed. All right, so we look at where the x-intercepts. The x-intercepts happen when the output, when the y is 0. And to find that, we set the numerator equal to 0. We look for the y-intercepts. So to find the y-intercepts, we find when x is 0. We look for the vertical asymptotes. So what happens when the denominator is 0? So we look for the intermediate behavior. And then we're going to make these little charts just to officially determine what is happening to this graph as we approach from the right and as we approach from the left-hand side of our vertical asymptotes. Okay, next class, we'll talk about our end behavior model, and then we'll get a lot of practice. So let me know if you have questions. I will see you guys next time. Bye.